everybody, welcome to CMECP Corner. Welcome, join me for a special Saturday edition. Welcome to the CMECP studio. And we are really excited about things that are going to be coming out in 2023 here with the change in the CMECP program. But today we're going to talk electrical safety. So I've got to kind of talk about electrical safety for everybody out there. Kind of one of those things that are really geared to the CMECPs, all of the CMECPs that are out there and those that are in the process of becoming a CMECP. Before we get into the presentation about electrical safety and some electrical hazards and some data, I will let you know that the presentation that we're going to do is going to be a part of an overall electrical safety NFPA 70E and OSHA thing that we're going to be doing in the next couple months. So that's going to exclusively be available over on the Fast Tracks tube. So if you're interested in the electrical safety, OSHA training, all that kind of stuff, that's where you're going to go for that. But we want to kind of get into the basics and talk about that today. But before I get into that, I want to give you some announcements about the CMECP program. We have quite a few candidates that are moving through the program. Just recently, we had 2 new graduates, Bill Butts and Jay Grunberg. Welcome to the family. And we've got others that are moving through it. We've got some candidates, David, who is getting ready to finish his 6-month period, and he's getting ready to do the proctored exam. So that's exciting to get David into that. So it's a select group. We don't let everybody through. You have to qualify. It's no free pass. You have to earn it. So that's what's interesting about the CMECP. It's not something you can buy your way into. Okay, once you get in, you're going to have to perform, and that's the importance of that program. CMECP. It's called Certified Master Electrical Code Professional. Okay. All right. So if you want more information on that, then just go to cmecp.org. You can get all the information you want on that. And of course, if you have any questions, feel free to bring that up. Again, I see Jay in the house. One of our CMECPs is present. So again, amazing. Congratulations, Jay, for making it through that process. If anybody out there wants to know whether or not that process is difficult or hard, ask Jay. Jay has my full authority to give an unbiased review of the program. He took every single second of it to do it, and and excelled at it and did a wonderful job. So, all right, everybody out there. So we're going to talk a little bit about something today that people get very complacent about. They typically take electricity for granted. Jay, it's like he says, guys, I'll show you what Jay said here. Basically, to focus on the program, he had to shut off his social media for 6 months. He stopped the little ticking and really had to focus on the program. But it can be done, right? Can achieve it. All right, so let's go on and get into today's little lesson. But if you have any questions, feel free to post them in the chat, and I'm more than happy. I'll share them on the screen, and we can just discuss anything you want about the program. But we're going to talk electrical safety today, so let's go on and get that started here. Okay, but anytime, feel free to ask any questions you want. If you're visiting me and you want questions about any of our other stuff, Fast Tracks programs, when the new 2023 is coming out, anything you want, feel free to put it in the chat, and I will do my best to try to answer that for you. All right, so Chapter 1. Now, this is going to be part of an ongoing series for electrical safety, OSHA and NFPA 70E that's going to be exclusive to Fast Tracks Tube, but we like to give the introduction. So we're going to do Chapter 1 here, kind of talk about it a little bit. And some of the data we're going to show is a couple years old, but we will slowly be updating this data, but it's still relevant to understanding electrical safety and things that we take for granted. I see a lot of stuff, for example, on TikToks and Instagrams and all of people taking safety kind of tongue-in-cheek, not overly serious about it. And of course, Jay does videos and he'll talk about talking with live stuff, but Jay's a professional. We all know that when you're working on a circuit, typically you shut it down. There's no need to work on anything live. We don't need to be macho, right? Although people do it. And if you're going to do it, you're going to have to prepare for that to work with it. Because again, Jay, for example, has wonderful children, a loving wife. The last thing that he'd want to do is put them through the pain of, and I think it's more pain for me if I get shocked and killed. I can only think, obviously it's painful for me, but it's over. But the pain for the family lingers on. They have the memories that are lost. I mean, you're gone, you're gone, you're gone. They have to deal with the aftermath, and nobody'd want to put their family through that. So one of the messages that I tell people about safety all the time, and I speak about electrical safety and used to speak a lot about it. I don't do much 70E stuff, but I will tell you, don't underestimate what the impact of our foolishness can be on other people. And I don't say that to turn anybody off, to upset anybody. The reality is, I can't imagine what my wife would go through if me doing something foolish that I could have prevented resulted in my death or disfigurement or the non-ability to interact with people. What would it be like, right? So again, don't underestimate that. All right, so as you can see here, we're going to talk electrical hazards and the basic electrical safety concepts, talk about some definitions and how to recognize hazards and whatnot. So objectives of today's presentation is a couple things here. We're going to identify the difference between OSHA regulations and NFPA 70E standards. We're going to discuss the meetings and actions involved in the NFPA consensus process, which I am a part of. If you're not familiar with that, explain the efforts of electrical related injury, the effects, of electrical related injuries. Okay, so we've got some data and we've got some hardcore data that we'll be sharing that you might be shocked, no pun intended, by. Describe the recognized hazards associated with the use of electricity. Sometimes we take this for granted. We think it's just common sense. But again, it's one of those things that you really have to think about. And so in this application, we want to make sure that we can recognize those hazards, deal with them, isolate them, and reduce our risk. Okay. Explain the importance of arc-rated clothing and define incident energy. Now, a lot of people think if you're working on residential, a light commercial, that none of these things will apply to you. That is simply not true. It doesn't take but 1/10 of an amp to actually kill you if you get bonded right. So every time you work at something, I mean, if any electrician says, "Oh, I've been shocked," you really shouldn't get shocked as an electrician if you follow proper procedures, right? You shut things down and you isolate them and you don't work on energized equipment. Unless you're troubleshooting something or using voltmeters, and then you're going to use insulated probes, and you have to be very careful what you're doing, right? So again, I just caution people, don't always watch the TikToks, the Instagrams, the YouTubes, and see things that people do and really think that that's okay, because a lot of the stuff that you see on that is not okay. All right. So let's talk about it. Arc flash hazards. Okay. When the primary disconnects of a circuit breaker are about to make or break with an energized bus, and again, in this picture right here, you see the bus right here on the right, and this is an example of a circuit breaker which is making or breaking, so it slides on. You see the little wear marks here on the right here. It on and off of the actual bus. The moment under load, you break that contact, you create potential arc, right? And so the intensity of that arc is very much having to do with the amount of current that's running through it, all those things being relevant. So when the primary disconnect of a circuit breaker are about to make or break with an energized bus, there is an increased risk of an arc flash, obviously. Now, inside of electrical equipment, it's contained within the enclosure, things like that. Or if we're working with bigger equipment, we have protective equipment on, in order to, just in case something goes wrong during that make or break process. Now, since there's no arc extinguisher, an upstream overcurrent protected device would have to clear the fault. So we have an arc, something takes place, upstream, clear the arc. Now, in dwellings, for example, we have arc fault circuit interrupters, right? And they detect arcs of certain characteristics. And we will be doing some videos that'll be available on Fast Track's Tube. So I encourage you to subscribe that we will be talking about 1699. That's the UL standard. We'll be talking about arc flash circuit interrupters, my evolving opinion of those, and things like that. Okay, so it's kind of what we've got going on. Now, a purchasing agent or an individual purchaser may mistake PPE to be arc rated just by how it looks at some of the things that they kind of look at, and they make a mistake and say, well, what's rated, what's not rated. You have to be very careful when you look at the actual equipment and all of the labels that are on it, to be very careful. So you also want to make sure that you speak with the people that manufacture these products. Don't just buy them blindly, making sure that they're available in the calorie rating that you're going to be exposing them to. So you just don't go blindly buying them, because they're not all created equal. You see the label example C on the right says fabric made in China. Okay, it has ATPV ratings on it. It gives you this, but you have to be very careful of the rating class. So the moral of this is to be very cautious of who and where you buy your PPE equipment from, especially with the labels. Okay, and also making sure that, and we go deeper in this on our program as we get further into it on our Fast Tracks Tube channel in this series. So this is an overview, but making sure that you have the proper class rating for the proper environment that you're working with. That is so critically important. You just can't throw anything on and think that you're protected. So that's something that's very important to remember. Right? So be careful where you buy it, what manufacturer, and be careful how you buy something. So you might buy a shirt that's rated differently, for example, than maybe the pants or something. And one might be rated for the environment, one might not be. So be careful of that. All right, so one of the things that we look at is, and let's see here, hold on for a second, folks. Let me do something real quick. Bear with me real quick. Let me see if I can, hold on for a second. I want to see if I can't grab something else. Bear with me here. I'm going to grab something else from this, and I want to share with us. Let's see here. Let's see here if I can get it. Let's see here. Hold on for a second. Oh, bear with me here, so I can try to see if I can get what I'm trying to get. Hold on. Trying to see if I can find one of the pictures that I had. No, that's not it. And I'm screwing up my stream here. Hold on for a second here. I'm trying to. There we go. Maybe that'll work. Let's see. What does that look like? Bear with me, folks. I decided I wanted to be able to. Let's see here. Let me see if I can find it. Yeah, it's not going to let me do it. Bear with me. Okay, there we go. It's fine. All right, so let me get back to it. I thought maybe it would have something additional on it. Bear with me here. I can get one more thing here. There we go. All right, folks. I just wanted to get one more thing on this so I can maybe share it with you, if it would let me. Okay. There we go. There we go. All right. Sorry about that, folks. I want to make sure I can share all the screens with you. So let's go back real quick to this one here. So I want to share it. So if you're looking at this material that you're buying from somebody, be aware of the mismatch. Okay. So in here, example, you look at A. So example A, it clearly has an HRC2 rating and a 9.6 ATP rating on the pocket label. It also shows NFPA 2112. Okay, so you see the NFPA 2112 marking on that. But it says nothing of NFPA 70E or ASTM F1506. It says nothing about that. If we're using NFPA 70E and some of the requirements in NFPA 70E, this piece of equipment doesn't really say anything about that on it. It's just making reference to 2112. All right. Now, also, if you go and look at the example C, it shows an ATPV, and it's really hard for you to see it, 9.6, but it has no documentation to support it. So you bought it, but there's nothing to support it. So most of the equipment you'll buy with the PPE rating on it will have the proper ratings on it. It'll give you the standard document that this is based on and everything like that. Okay. Now, PPE can be rated with both NFPA 2112 and ASTM F1506, but both standards must be listed on the label. Okay. So always look for that when you're checking out your equipment. All right, so we're looking at this rating here. So per NFPA 70E, so if you kind of look at how this goes, it says an arc flash boundary is an approach limit at a distance from a protective arc source within which a person could receive a second-degree burn if an electrical arc flash were to occur. The second-degree burn discussed is the onset of the second-degree burn equal to 1.2 calories per centimeter squared for 1 second. So at 1 second, you can obtain this type of burn, a second-degree burn, which is a survivable burn, okay? It's curable burn. We don't want that burn, but it is a curable burn, okay? Now, there may be small amounts of blistering at the skin on a 1.2 calorie exposure for 1 full second, but again, not widespread, just location spot point blistering. Again, that's a survivable, and that is a second-degree burn at 1.2 calories per centimeter squared for 1 second, okay? Now, large areas of blistering increase the likelihood of infection. So the small blistering that you might get from this type of exposure for 1 second, and we're going to talk about why the calorie suits go much higher than this. This is considered survivable, right? So if you look at the actual exposure in seconds, as it goes up the scale, you can hardly see it. But if you go right here in my mouse, here is the energy at right there at about 1.2 right here, just above the 1, and it comes over right here at 1 second, right there, okay? And as you can see, the incident energy going up right there at that point for 1 second, that's about where the 1.2 calories per centimeter square is, and you're going to receive curable second-degree burns, okay? But typically, when you have a lot more exposure, the blistering, if it's severe, then you have the chance of infection, okay? And you break those blisters, it even becomes more. So while you might not die from it, it's very uncomfortable and infection could set in at that point. It's best to have safe work practices. And this is even at this level, it could be your eyes. This is minimum exposure, okay? And it causes the blistering. Depending on where you get it, it can be quite devastating. So this is why, and this is something that can take place even in a residential setting if you're not very careful, okay, of that energy, all right? So this is why we create different things. Even in commercial applications, we have to increase the boundaries, protective boundaries. We have to have barriers or barrier tapes to create distances between the exposure. And that way we kind of are limiting the exposure. Now, again, 1.2 calories per centimeter squared for 1 second does cause second-degree burns, but they're typically classified as a curable second-degree burn. Now, I'm not so sure how well you can see this, and if I blow it up, it probably doesn't, it's not going to allow me to do this. But what we want to talk about here is this is electric shock, and I've got multiple screens going, folks. So camera's in the center, but I've got to look at my screen so I can read them better. Electric shock is the leading cause of electrical related injuries, but electrical burns injuries are more serious, okay? So electric shock is one thing you probably, if you survive it, but the actual burns that result from the shock can be more serious long term. So if you look at this table, and this came from ESFI. If you're not familiar with ESFI, that is an organization. It's kind of a wing. It's the Electrical Safety Foundation International. It's kind of a wing underneath of NEMA, if you will. And if you look at that, their website showed these data points, and I'll kind of point these data points out to you. So in this table, EFSI is an organization that uses the latest data from the Bureau of Labor Statistics, BLS, you've heard us talk about that, and OSHA. They compile this data so that it makes the people that work with electricity and safety professionals that might work in your company help to make you aware of the potential hazards that you have. So kind of looking at this data, it says provided information to the general public. They also collect and publish on their website on esfi.org. So I encourage you, go to esfi.org if you're the safety person for your company or you're the head of your company, right? That you make sure, because ultimately at the end of the day, as the owner, you're overall responsible to make sure that all of your people have proper PPE and it can work with it properly, and train them on how to use it. And they have a certain amount of responsibility, but you do as well as the employer. And there's different classes of employers that we'll look at, okay? So, see, we have a question. Let's see what this question is. How do electrical codes that you are referring affect building an app or designing a solar planes? I have no idea what you're talking about. Sorry, I'm not sure. I'm not sure what you're talking about, so I can't answer that question. All right, so let's look at some of the private sector. So if you look at, you can't really see the chart. Now this goes up to 2018, so there is newer data that's out there, right? So you look exposure to electricity. If you look at the data here, electrocutions and electrical shock in 2018, we'll just go to the recent, but again, there are updated values available. Exposed to electricity for, let's see here, direct exposure to electricity, and you've got 4, let's see here, indirect exposure to electricity, 220 volts or less, 2, and then indirect exposure to electrical greater than 220 volts, 22. All right. So this kind of talks about the shocks and what happens. Now, any of this is serious, but this chart has to do with days away from work. So losing work from actually electrical injuries from shock and burn. How many days do you lose work? So electrician is shock in 2018. You can't see hardly this column over here. That's what we'll focus on. That you had indirect exposure and you have direct exposure, somebody working directly on it. Say direct exposure to electricity greater than 220 volts, 7 days from work is the median days away from work due to whether electrical shock. Now, obviously, if you're electrocuted, we don't even need to count the days, because if you get electrocuted, you're not coming back to work, right? But this is a kind of data that we'll get deeper into as we move into the 70E programs that we have. But this, again, is just trying to realize that for a company, lost work, employees away from work is serious business, especially if they're shocked, okay? Being away from work is critical because, again, it reduces productivity and people aren't making money. But again, the one that's really staggering was the indirect exposure. Right? The indirect exposure, the median days away from work was 22 days for that indirect exposure. Not so much the direct exposure, but the indirect exposure resulted in being away from work. So you're working on something indirectly, you're exposed to it, and at the end of the day, it could be longer than 22. For you, it could be your life. So, but that was indirect exposure, is quite interesting. All right. So looking at this little chart here, according to ESFI's latest statistics, and latest being 2018, although they do have some updated stuff, so we will be updating these values, but they stay pretty consistent here, is electrical shock accounts for 89.61% of all electrical fatalities. Fatalities from burns were 2.79%. So if you look here, you see this area here, right? And we're talking about fatalities. So when you did get shocked, it looked like 89.61% was fatal. Now, I know electricians that work on things all the time and get a little bit of a shock, and they don't take that, they kind of take that for granted. But when you start looking at what happened when it came to fatalities, electrical shock accounted for, again, 89.61% of all overall electrical fatalities, right? Talking about dislocation, cuts, laceration, bruises, contusions, fractures, concussions, and burning and scalding. The percentages here, by far, the number of fatalities when it came to electric shock, when it happened, it was 89% plus fatal. So you didn't get a second chance. So when electricians working on a project, and I want to employ to people something that even though you are working maybe in residential or light commercial and you think it's not going to happen to me, if it only takes 1/10 of an amp to kill you, if you're put in the right position. Okay, so yeah, usually we have work boots with rubber soles. Usually we're not touching two bonded parts. We're very careful when we're in panels. We don't make sure that we go in with both hands and get shocked so that the current can travel across the heart. We try to be as careful as we can, but I just want to implore you, it only takes a small amount to cause severe damage, if not death, and then of course the aftermath to the family. Why would you play? If I'm an electrician and I go into an electrical panel, I take it everything. I treat everything as if it was live. Okay, and I don't just use a tick tester. Okay, I check with the voltmeter, or if I'm doing a tick tester, I check something that's I know is live, and then I check and see whether or not it's on. I just want to be sure, right? And again, electricians think they're indestructible, so I get it. So here's another ESFI statistic, and it's 2018. And of course, there are some newer data that we'll share. I'm not going to share that in this free version. We'll be updating this for the other versions, but this is kind of to give you an understanding. ESFI reports that there were 160 electrical fatalities in 2018. One fatality from electricity is too many. One. There is no reason to have 160 electrical fatalities in 2011. Okay, so if you look in here, that it increased 18% from 2017. So they also report that there were no fatalities from electrical burns in 2018. So the burns didn't result in death, okay? But there was, again, 160. Now, this was a steady drop as we started having more education, as you can see, started dropping in 2007 and pretty much went down. And then in 2018, it started going up again. So we'll see what happens in 2019, 2020, 2021, although we know COVID kicked in and probably resulted in some numbers that are pretty much, we'd have to say, skewed numbers based on that because of the lack of in the field. So we'll be looking at more relevant data from 2022 in some upcoming episodes. So, but again, these all pretty much stand true. And even here at 160, that is 160 too many. Okay, so I would tell you, for your employees, really spend the time to make sure that they're educated on safety and don't need to be heroes and those types of things. Because again, it can be devastating for not just them, but for the families and everybody around them. All right, so this study here, there are, in this study here, there was 1,560 non-fatal. So we had 160 fatal, but there was 1,560 non-fatal electrical injuries in 2018. This is a decrease of 29% from 2017. So maybe we chalk this up into education. People are starting to learn to be more cautious in how they work around things. But these are non-fatal electrical injuries. This could be cuts, bruises, burns, falling, things like that didn't result in a death. And good news is the trend seems to be moving down here. And obviously in 2018, it was about the lowest it's been in, I guess that's 20 years or so or more. So that's a good trend, right? That it starts going down. So ESFI also created a chart showing fatalities from electric shock versus electric burns by selected industries from 2003 to 2018. This particular chart you see on the screen does not differentiate between arc flash and arc burns caused by current flowing through the body. Why is that? Well, because OSHA does not record arc flash injuries as a separate item. Okay, it's all inclusive. So you kind of have to work with this data. But if you look right here, you see in the construction industry, is if you're in electrical, you're probably in deep into the construction industry. And so looking at it as a whole, you've got electric shocks, 4,510. Okay, these are fatalities from electric shock versus fatalities from the burn. So from the shock, we had total 4,510. Okay, and then from the electric burns, you had 5,530. Of the industry, it looks, obviously the construction industry is heavily involved in that. They obviously work with it every day. So it's much more exposure there. But I think what's interesting is if you kind of look down and some of the listing here, notice the utilities. So the utilities, the electric shock is less right here. It's only 350 versus electrical burns is 10,080. So they have less fatalities from the shock, but more of their fatalities come from the electric burn, probably due to the amount of energy that's exposed on the utility side than it is from the actual electric shock. So they're very cautious about how they approach it. But again, if a blast takes place, then the burns seem to be the detriment to them. So if you kind of look at how it goes, it's quite interesting to see the change in it. So this right here, this is fatalities by events from 2003 to 2018. So the CDC, or the Center for Disease Control and Prevention, and the National Institute for Occupational Safety and Health, which is NOSH, I guess that's what it's called, NIOSH, have presented several informative papers concerning accident statistics at the IEEE Industry Applications Society, IAS, I have a member of that, and Electrical Safety Workshop, and the Petroleum and Chemical Industry Committee, PCIC, conference. In 2006, James Cowley, a PE at the CDC, and Gerald Homsey, I guess that's his name, PE at the NOSH, presented their paper. And the paper was entitled Trends in Electrical Injuries from 1992 to 2002 paper. And you can look that up. If you're looking up the paper or you want to see the document, it is PCIC 2006-38. And you could probably search for that on the IEEE website if you're interested in that. And basically, currently Cawley is his name, C-A-W-L-E-Y, currently works for the ESFI, and I don't know if he does as of 2023, but he did when this publication came out and these data stats came out, and they continue to update these stats. So if you look, you can't hardly see these stats. I'm sure it's really hard to see. But if you look down, and it's quite interesting here, struck by an object, deaths, okay, fatalities, right? If you look by struck by an object, you had 8,325 fatalities. You had 566 fatalities in 2018. Okay. And if I'm looking down this list to contact with or exposure to electric current, okay, it's 2,948, or that's the 160 that we received, the fatalities from 2018. We saw that data earlier. So that's where that data is. But if you look at it here, assaults or violent acts, 828, transportation, 1,841. This is excluding water, rail, and air. So that's obviously vehicle deaths, fatalities from death. But I tell you, look at some of the things that are lower. You can't hardly see it, but right here, aircrafts, 133 in 2018 deaths from airplane. So you were much more likely to die from contact or exposure to electricity than you were in an airplane, for example, in 2018. We had more deaths from electricity, fatalities, than they had in airplane deaths. Explosions, only 71. Railway, 48. Okay, so at the end of the day, 161 is something that we should work on getting off of this list. And we can only do that by being extra careful, extra safe, proper PPE, don't take unnecessary risks. No need to work on things live, don't need to be a Superman. Okay, and I know some people out there will say, well, I've done it for years. Well, you do you, bro, but look, it's not worth it. You know, bro, so why mess with it? So now I take the chance. Interesting stats from ESFI. So here is one, 2018, overhead power line fatalities accounted for 50% of all electrical fatalities, overhead power lines. So for the first time since safety stats have been recorded, overhead power line fatalities accounted for 50%, that's 61 of electrical fatalities. In the past, overhead lines accounted for about 40% in electrical fatalities. This is a noticeable increase. Now, this can come from many things. This could come from high power lines coming down during storm, people getting shocked during a storm, people working on high power lines, all those type of things. But this is a increase in fatalities from overhead power lines. Right? So if you kind of look at this number of fatalities, if you look in 2018 right here, you've got overhead power lines, you've got, this case, 61. And then the other electrical fatalities, 61 down here. Okay, so in 2018, so again, just about 50% from that. So electricians, so in this case, it is expected that electrical workers will be exposed to electro hazards. Obviously, electricians, you're going to be doing work on electrical stuff all the time. We get it. That's your job. Electricians got to get in there, whether you're troubleshooting or you're working on things. Now, typically like rough-ins, there's really, the risk is what? You don't have much of a risk. If you're an electrician and you're putting in the equipment, the switch gear, you're putting in the panels in a building, it's dead. There's no power in there yet. You're just running all the circuits. That's not where your risk is. Your other risk there would be falling, tripping, things like that, overlifting things and hurting your back, things like falling off lifts. Yeah, but once you start putting the equipment in, you start energizing it, and you start putting everything in, powering it up, or if you're going into service, update, and maintenance, here's where your risks increase, and here's where we have to have the PPE. Here's where we have to make sure we are protected. Make sure we have the gloves on, face protection, eye protection, all those type of things as we start energizing the buildings moving on. So in this study here, it just points out that of the sector of individuals that are going to be involved in electricity, which is higher at risk of the exposure? Well, obviously on the list right here, electricians are at the top. And again, when it comes to fatalities, again, electricians, there's no reason for our brethren to be killed, okay, from working with electricity. If you do it properly, you follow everything right. When people say, well, I'd never do that or I'd never do this, then why in the hell do we have these fatalities? These is all preventable if you practice lockout, tag out, if you practice safe principles of working with electricity. This is all preventable. You don't think these people wanted to die, do you? No, it's just they did not take it serious, or accidents happen and they weren't prepared for it. But if you look at this list, and it's kind of hard for you to see it, but you'll see down the list, electricians is by far the greatest risk here. Now you've got some truck drivers, farm workers, plumbers, pipe fitters, steam fitters, and whatever. Again, down here, 11, very, very low compared to, look, even roofers, 27. Okay, apprentices, 31. So you add the electrician plus you add the apprentices that are 31. Maybe the apprentices weren't trained properly. Maybe you didn't have safety meetings on your project, right? If I was somebody that owned a company, for example, like Jay, even though the main majority they do is residential, I would make it a point to make sure at least once a week, get on a Zoom call or whatever and meet with all the project managers and emphasize safety. Why? Because it's Jay's company's liability if somebody does something and doesn't think before they do it. And for example, a PM could come in contact with anything, and they have to make sure they don't, kind of try to do something that could cause hazard to them or somebody else. So always thinking about those things are critically important. So again, it's staggering to see that we had to lose 150 electricians directly due to this between 2011 and 2018. Okay. Now, as you can look at this chart, for what you can see, it may sound surprising, but check it out. Groundskeepers, gardeners, truck drivers, and administrators are at a higher than average risk for electrocution. Seems odd, doesn't it? This is because these workers are encountering electrical lines in the ground, running around flower beds, all over the place. They're coming in contact with it on a daily basis during the course of their normal job. And that's how they get electrocuted. It's not like they're going out and doing electrical work. They're just involved with it. So when an electrician runs the circuits, this is why it's so important that we follow the code. This is why we have proper depth of barrel. This is why we do what we do in the NEC, because it's not just so much us getting the job done, but it's the other people that we'll encounter. I have people all the time say, why do I got to do this in a house? Why do I got to do that in a house? And it's not about the owner that's there now. It's not about what they want. It's not about what you want. It's about what down the road somebody that might own this house might be exposed to. So that's why we have to follow a minimum safety standard of the NEC. Okay. They might not want that receptacle there, but they're going to get that receptacle there if it's required by code. Okay. Whether they want it or not. So when it comes to groundskeepers, other people, they're going to be interacting with our electrical. And if it's not done right, or it's unsafe, or it exposes somebody, like grounding and bonding. I know that electricity works. And those that don't have a firm grasp of grounding and bonding, maybe it works when you leave, but you're putting other people at risk if it's improper case to neutrals downstream, if it's potentially energized metal parts. It works. Electricity still just tries to work. That's the amazing thing about it. But you have to think about the next person. So that's why it's kind of this moral thing to always make sure it's done right. Make sure that you tighten everything that you're supposed to. Make sure that you have bonding jumpers where they're supposed to be. Make sure you do it right, because it's not about you. It's not about the current it's about the future. What could go wrong? That type of scenario. All right. So a couple other things about this chart. For example, groundskeepers may encounter electric lines when they're trimming the trees, or even digging holes for a new plant or bush or tree. Truck drivers may raise their boxes or their apparatus into overhead lines on a construction site. Then they don't realize where they're at, proximity, and they raise their bed up into power lines. Those type of things. They're not working with it. They're just not paying attention, but it's always there, right? Gardeners, again, maybe they're working around and there's buried lines underground, landscape lighting or whatnot, and they come in contact with it. And remember, folks, it only takes 1/10 of an amp to kill you. What if you put a circuit in and you put lighting, but you're cutting a corner and your boss tells you, don't worry about putting in that GFCI. And then the poor landscaper cuts into it and gets shocked. Or he's digging in, he sees something, he hits something, he reaches in, he's got his hand on the ground, and he reaches in, he's trying to clear the dirt away, and his hand comes in contact with the 120 volt line. And then the current goes through him, through his hand, back to ground, and he gets electrocuted. Everybody's resistance is a little different, okay? Their tolerance is a little different. Who's at fault? That's why you put the GFCI on it. It's not the manufacturers trying to make money from it. It's just, that's the way it is. That's what we're going to try to use to protect somebody. So again, those people, even though electricians are obviously the highest on this list, there is other exposure here that people can get killed from electricity, right? That are not necessarily just electricians. And we have to think about them when we do our circuits. So at the 2004 IEEE IAS Electrical Safety Workshop, a Professor Trakofler, I think it's Trakofler, Trakofler, right, did a presentation and did a paper, and it was called Non-Contact Electric Arc Induced Injuries in the Mining Industry. Okay, so may not directly affect most of us. We don't work in the mines, but it was the contents of the study that was the most important, that what was presented, right? So what presented was a multiple disciplinary approach was applied to the testing. And even though the results shown were focused on the mining industry, okay, so we get it, the results of the CDC or the study could apply to most electrical workers. So even though it was focused on the mining industry, it really didn't matter. It could apply to all of the electrical industry overall because the data was so closely related, right? So for example, 24%, if you look at this study, and I know it's hard to see, I will point it out. We're looking at the red there. 24% of the incidents involve electrical workers occurred during what? Troubleshooting or voltage testing activities, folks, right here. So of the injuries involved in electrical work, when they did the study, it had to do with people taking testing, taking measurements, working on a system that had trouble on it. And those should be the ones that you really take precautions, proper PPE, making sure you're wearing the gloves when you're testing, okay? Eye protection, even during the testing phase. Because whether this was done in the mine industry really doesn't matter because it's electrical in general and it has to do with testing and troubleshooting. It can apply to the entire industry, right? So again, when you're going into even an electrical panel in residential applications, right? I mean, we all want to be super people. We all think it'll never happen to us, and I hope it never does. But when you start sticking your meter in there and you're testing things, really have eye protection on and just make sure when you're testing, if it's live. Now, we've gone a long way in the electrical industry now. We protect the buses, services. We'll put the little protective covers on it so that the live part's up there. But that bus is live unless you turn off the main. If you turn off the main and you're working below, it's kind of hard to troubleshoot, right? Got to be live to troubleshoot. So as far as 70E is concerned, when you're working on equipment like that, you need to have certain levels of PPE, depending on the risk assessment. So why would you want to take that for granted? Because it doesn't take but a second for something to go wrong. And again, you don't get second chances. I happen to know a personal story of a gentleman who was doing nothing but testing a 122 40-volt panel. And during that testing, something happened and an arc occurred and a little piece of molten metal shot out and hit him in the eye. And he ended up being blind in that eye. It just happened just like that. Your whole life changed. Okay? You might think it never happened. For him, it happened. And it could happen to anybody. Why risk it? Is it really worth it? Do we really need? I wear these are glasses that if I'm in a panel, I'm always going to have something protecting my eyes. And I'm going to use non-contact devices. And I'm going to be very careful, very cautious around things like that. So again, we take it for granted, but don't. I'd hate to hear of anybody getting hurt simply by being too casual when you're working with electrical equipment, any electrical equipment, unless you can lock it out, tag it out, and you know for 100% for sure that it is shut down. Don't take any risks. But if you can see right here, the area, the testing they did, 24%, I'll bring it back up here, 24% right here. Failure in normal operation down here, 19%. In normal operation, something just failed. So you never know when something's going to happen, but 90%, okay, of electrical workers that had electrical accidents, 19%, the equipment was working fine when they were working on it and just something happened, okay? So let's see here. Maintenance, 5%. Installation, 2%. Let's see here. Repair, 18%. So they were repairing something and then an injury occurred. It can happen at any time, but it is staggering that 24% had to do with troubleshooting and simple voltage testing result in such a high level of injury. Nobody goes into that thinking you're going to be injured. You're just testing for voltage. You're just testing for a circuit. So quite astonishing that would be so high, in my opinion. All right, now let's talk about electric shock a little bit. Everybody's probably familiar with Charles Dalzell, he was basically the godfather of GFCI, right? So you look at this table right here and understand, again, how simplistic it can be when you get shocked and what could happen. So the severity of electric shock depends on the amount of electric current through the body and the length of time that body is exposed to that current. So the quicker that the overcurrent device, the quicker that the GFCI can shut down, the less exposure you have. And so if you kind of look at this chart here, you're dealing in milliamps, okay, 1,000th of an amp. Okay, very small amount. I tell people all the time, that receptacle on your countertop in the kitchen, 20 amp, can kill you many times over. When we electrocute people in the electric chair and we're pumping 50,000 volts to them, I could do that with 120 volts if they want to, but it's going to take a while and it's going to be painful, but I can get the job done. The thing is, when we do that in electrocutions, we like shock and awe. We like the eyes popping out. We like the smoke coming off the head. We like to try to say that that's humane as quick as possible, okay? But at the end of the day, the same results can come from a simple 120 volt circuit, right? So if you look at it here, the stats, here is 3 to 7 milliamps. It's painful sensation. And again, remember this 3 to 7, that 5 milliamp is what the GFCIs, Class A GFCIs, that's where they're sitting, right? So a GFCI Class A is designed to do what? 4 and less and 6 and more. We call it 5 nominal. So they're 5 milliamps. So at 4 and less, they're not supposed to activate. At 6 and greater, they're supposed to make sure they activate. So that bridge is right there at 5. So it's kind of, for the manufacturers, you got a little bit of left and right that you can move at that 5 nominal, but that's what we all base it on. But that's a painful sensation. If you can keep it to 7 milliamps, for example, and you had that exposure, it's just painful sensation, but it's probably not going to kill you. However, as you go down, you look at something as simple as 10 to 16 milliamps. Again, way below what you would see at a receptacle, okay? A milliamp is 1,000th of an amp. So 10 to 16 milliamps, muscles contract. So when they contract, let's say you're crawling in a crawl space and maybe a metal pipe is energized or somebody bonded improperly, and now you're crawling underneath there and you put your hand up on this pipe to support yourself as you're trying to get under it, that's all it takes. I can tell you of an incident where an individual and his helper were both electrocuted by that scenario, by these energized metal pipes underneath in a crawl space because somebody improperly bonded the lines thinking they were required to bond them, but they did everything improperly and they were energized. Okay, well, everything was sitting fine and dandy until that gentleman came in contact with it. And then his helper reached over to try to help and they came. So at 10 to 16 milliamps, the muscles will contract. And that increases the exposure because they can't let go. And so you're locked on. Have you heard the old story when you're touching the panel or checking it, use the backside? Okay. And you touch it. Okay. Why are we doing that? Because there's no way we can get locked on. And if we get a shock, we could easily pull away. Whereas if I grab something, it could lock and cause the muscles to contract, and then I stay connected to it. If you've seen the videos on YouTube, and you can Google them, they're pretty, they're pretty morbid videos, but it shows people that touch something. There's a guy that's dancing on the top of a truck in another country, and he reaches up and grabs it, and he's locked on. He can't let go. He doesn't have a choice. The muscles contract, and that's it. The longer that he stays contact to it, that's it. There's no recovering from that, okay? So that's a small threshold, folks. And remember, put this in perspective. 1 milliamp is 1,000th of an amp. We're only talking 10 to 16 milliamps. We're not even anywhere near 1 amp. And it can cause the muscles to contract, and it increases that exposure. You start to perspire. The resistance starts to drop. And now the amount of current in milliamps will increase. And next we look at, it gets up to about 30 milliamps. And here, that's where respiratory paralysis takes place. You're unable to breathe, right? And it kind of locks up internally. And you will actually starve the brain of oxygen. And it's not long after that that you're going to die. But because you're locked into it, you stay connected to it, your body resistance reduces. You start to sweat, perspire. That resistance that's inherent to us starts to be reduced. So current starts to flow a little bit easier. And so now you look at what happens if you increase that to 75 milliamps. Again, we're way even below 1 amp. And here you're locked on for 5 seconds, or if you're locked on to 100 milliamps for 2.5 seconds, 2.5 seconds. And as you grab onto it, you could be at a lower milliamp level, but then as you perspire, that resistance will drop and the milliamps will rise. And again, the exposure increases. And that's where the longer you hold it, the longer you're on it, then all of a sudden you go into what's called ventricular fibrillation. So you've heard of defibrillators. They actually, and it's kind of ironic, it uses shock to shock the heart back into a normal rhythm. Because when you get into ventricular fibrillation, the heart's really fluttering and it's not able to pump any oxygen, any blood. So again, it is a matter of time before that's it. And all while this is going on, anybody around you that sees this could come in contact with you to help you. And that's the normal nature, right? For somebody to come and help you. What ends up happening is now they come in contact and they become a victim of it as well. And so that's what happened to the gentleman under the crawl space and his helper. And it was hours before anybody found them under there. The people that they were doing the repair work for started realizing they haven't seen the plumbers. They haven't seen them in a while. And that was a result of that. Okay? It's kind of a sad situation. But as you can see here, it doesn't take much. So anybody that says, oh yeah, I've been shocked. Well, you've been lucky. You're not bonded properly. Because if you were bonded properly, you wouldn't be able to talk about it. I know everybody's a Superman, but at the end of the day, it's still a very important for people to realize that electricity, it doesn't take a whole lot, right? Now, I was talking about the defibrillators. A lot of the sites, we have them at Encore Wire. A lot of job sites will have a defibrillator. You need to understand how to use them. They're very simple to use now. They basically come with a guide card and tell you where to put the sticks that you put on the body. They pretty much are available most job sites, but it's called an automated external defibrillator, AED, passes an electric current through the heart, causing the heart muscles to contract. The AED has been responsible for saving many lives that would have been lost through ventricular fibrillation. So it causes the heart to shock it, contract, and then off, it allows it to beat back into a normal rhythm, okay? The only practical way, folks, to correct this condition of ventricular fibrillation is by using an AED. That's the only way it's gonna happen. You're not gonna do pulmonary resuscitation. Once that heart starts going into that flutter, the only way to get it is to, again, how ironic, shock it back into rhythm, okay? So most of the commercial facilities, commercial job sites around the country, federal buildings, all of those are required to have an AED on site. If you're on a big construction site, and I challenge you, if you're the safety manager, go up and ask some of the people, do you know where the AED is? And see if they know where there's an AED, if there's even one on the site. There should be one on the site. And everybody should know how to work it. They're pretty straightforward and simple, but you should know where it's at, how to get to it, to be able to use it to put the heart back into a normal rhythm, okay? So it's pretty simple. It causes a shock to pass through, current to pass through the heart, cause the heart muscle to contract and briefly stop instead of defibrillating, going all this fibrillation, going crazy and not pumping anything. It causes it to stop. And when the current on the machine pulses out and stops, the heart will begin to beat normally again, unless it's been setting in a fibrillation state for too long, and then it won't do any good. So time is always of the essence for these pieces of equipment. All right, talking about shock and how it affects everybody differently. It does affect everybody differently. So it takes less electric current to produce the same effect in women than it does in men due to body size, composition differences, skin thicknesses, all those type of things. The calluses that women may or may not have. Bunch of differences that can mean whether or not a woman has a different rate of exposure than a man. And if you look at this chart, it might be hard to see. But if you look at it, it says, okay, number one, it says slight sensation on the hand, very slight. And we're talking milliamperes now. Now, direct current is 1 milliamp. Now, we're not going to talk direct current. You can see that on the left side. We're going to stick to alternating current, and we're going to stick to the 60 hertz because that's basically what we're going to be exposed to as electricians in the field. Typically 60 hertz. Amps, it might be 1,000 amp switchgear, 2,000 amp switchgear, 480 volts. It could be 120, 240. But what we're going to have is it's going to be a 60 hertz. Okay. So men, slight sensation on the hand, 0.4 milliamps. For women, it's 0.3, much more sensitive. Next, perception threshold. Median means when you get shocked, you actually really can feel it. The perception, you know it's there. For a man, it's 1.1. For a woman, it's 0.7. Much more sensitive for women to feel that perception of threshold of shock. Next, shock, not painful, and muscular control is not lost. Means you get shocked. It's not really painful. It's just a sensation that you get. You don't have the muscles contract. But for men, that threshold, it looks like it's 1.8 milliamperes. And for women, it's 1.2. Now, painful shock. Painful shock, and I am over here, folks. I'm about right here. It says painful shock, muscular control lost by 0.5%. All right. So you look for men, it is 9 milliamperes. And women, it is 6 milliamperes. So again, you do have that muscle control. Now, you might be saying, well, wait a minute. So that's 9 milliamperes. Luckily, a GFCI is going to stop this because that's at nominal 5 milliamperes. But in a circuit that's not GFCI protected, even at 9 milliamperes for a man or 6 milliamperes for a woman, even at that muscle control loss, it could be the result of a shock reactionary, right? It's painful. You could fall off a ladder, could fall off a lift, could fall off a platform. You could pull back, and maybe the hazard wasn't the shock, but maybe the hazard is the reaction to the shock. Maybe falling back into something. Maybe you're working next to, I don't know, a piece of spinning equipment, and you get that shock and you yank away, and then what happens? You end up yanking and you end up over involved in some other piece of equipment that could cause even worse harm to you, right? So that's kind of what could happen with that type of scenario. As we go down the list, you've got painful shock, let go threshold medium. For men, it's 16 milliamps. Again, folks, a milliamp is 1,000th of an amp. Okay, so 16 milliamps. And for women, it's 10.6. So that is the painful shock, the let go threshold where you're starting to not be able, you get onto something you can't let go. You're in it, and you're in it for the long haul, right? So those are important, but here's the one that I really like to focus on right here. Painful and severe shock, breathing difficulty, muscular control lost by 99.5%. Look at this, folks. For a man, 23 milliamps. Think about that. 23 milliamps, not even 1 amp. And for women, 15 milliamps. That is all it takes. Folks, again, we take electricity for granted, and I get it, right? You're saying, I'm an electrician, that would never happen to me. Every electrical branch circuit that you work with, if it's 15 amperes, even 1 amp, we're talking about milliamps. Think about that. There's enough in that receptacle, that 20 amp circuit, to kill you many times over, but yet we willingly go in and work on it. And sometimes our clines or side cutters, the insulated handles are beat to death. We don't take care of them. Why do you work on things live when you can shut it down? And if you're troubleshooting, just make sure you have gloves on and just make sure that you have comfortable gloves, because in bulky gloves, it makes it even worse. Comfortable gloves, okay? And insulated tools, insulated meters, testing. Why be a hero? Maybe put together your own little safety bag, little fanny pack or shoulder pack that has just a nice pair of your gloves and that you can wear, and your test equipment and your eye protection, and just say, you know what, I don't need to be a hero today. I'll just make sure that if I'm doing any testing, I put it on. I get it. People drop off watching. They're like, yeah, Todd, Paul's preaching safety. It'll never happen to you. God, I hope and I pray it never does happen to you. Even if you think you're Superman, and it'll never happen to you. When we're talking about milliamps, that's all we're talking about. That's all it takes. Electricity is an amazing thing. All right, so let's kind of get back into this. All right, so I don't need to go down here, but again, it obviously ventricular fibrillation, 3-second shock, again, at 100 milliamps for both men and women, then that's going to be a problem, because that's when the heart's going to go into ventricular fibrillation and you got a problem, right? So anyway, that's just some interesting stats to be aware of. Now, here's some other, all types of burn injuries accounted for 59% of the lost work days due to electrical injuries. So burns and loss of work days, loss of productivity. You didn't work, and many times you may or may not get paid for that work, depending on your negligence and what caused it to happen, that type of thing. So according to non-contact electric arc induced injuries in the mining industry, which is, again, going to be parallel with probably what you do. It's just a more controlled study was done on that industry with people dealing with electrical. It says of the 59% of non-contact electric arc burns accounted for 35%. Electric contact burns accounted for 12%, and other types of burns accounted for only 12%. Non-contact electric burns account for as much higher percentage than most people are aware. If such information were available from other industries, the seriousness of arc flash hazard could be determined much more easily. But as you can see here, this study was done on the mining industry, but it was presented at the 2004 IEEE IAS Electrical Safety Workshop. And as you can see here, 50% non-contact electric arc burns. Okay, these are burns from a flash. These are non-contact burns. So were they wearing PPE? And what were they doing? Are we aware of approach boundaries? Are we aware of everybody has to be trained on these, approaching it? Was that training done? Okay, but that's the burns that are associated. 59%, and the lost days is incredible, because it's loss of productivity. And if you're hurt, it could mean days that you spend in the hospital. Just interesting data to show you. So here is, according to that same paper that was presented in 2004, 34% of all electrical accidents involved recordable injuries were caused by component failure, and 19% were caused by equipment that failed in normal operation. So this is equipment that was running perfectly fine, and then all of a sudden, people might obviously were near it, checking on it. Maybe they were in there doing testing, and all of a sudden it appeared totally normal, but it was energized. And then all of a sudden it just component failure. You can't predict when something's going to fail. You go up into a panel, you never know when a surge might come in at that moment. When you're looking in a panel, you're opening the panel, even if it's simple 122 40 volt, when you're working in it, you don't know what's going to happen any given time. That's why it's so important to think about the glasses, protective eyewear, what you're doing at every minute, because you just don't know when something's going to happen. So it's quite astonishing, okay, to see that it was basically the amount of equipment that failed, right? That simply failed under normal operation. That is quite crazy to think about that 19% of that took place. Failed in a normal operating state. Quite interesting. It just tells me we don't take it for granted. Never take it for granted. Now, here, so arc-rated clothing is made specifically for electrical workers and is designed to protect from extreme heat for a brief moment or a brief amount of time. So when we think about the calorie suits, we think about the different calories that they're made in, they're designed to handle the incident energy immediately. When it came to, when we have an arc rating, we're worried about the amount of energy that's exposed, the heat that comes out from that incident. And you have your protective equipment on, whether you have your baklava, whether you have your actual suit on or whatnot, depending on the level of exposure. Now, the neat thing about NFPA 70E, as we will see in other episodes, you can do stuff that gets you closer to the equipment. You can do stuff that maybe if you have an engineered study done, or if you just want to follow what's in 70E, then you simply follow the recommendations that are in 70E. And again, it might be more restrictive than if you did some type of individual study, but at the end of the day, I recommend just following the 70E. But again, if you're an engineer who does this and designs these systems, then there are other ways to do this. But again, NFPA 70E is probably the easiest way, and it's the way I teach, because I want electricians to know that they have a document they can go to that's not an overly cumbersome document, but it does give proper guidelines for it. And anything that's not covered in there, then you can consult with a design engineer after that, somebody that's familiar with these locations and this type of energy. But following NFPA 70E is going to be what I recommend right from the get-go. All right, so the intent of NFPA 70E is for electrical workers to wear clothing specifically designed and rated for its use, i.e. arc ratings, as opposed to firefighters, steel workers, and other workers who must also wear flame-retardant FR clothing. This is because the heat created by an arc flash is extreme, but it's only momentary. Okay, it's not long-term exposure like a fireman, things like that have to expose you to it. So while the hazards faced by other workers wearing non-arc rated FR clothing are typically of a lower temperature for longer duration, okay, so FR rated shirts, clothing, that's for duration, longer duration. When you're talking about an arc rating, we're talking about extreme heat for a brief moment in time. It's not long sustained. And so the different calorie ratings and the different arc ratings, all the stuff that you see in this equipment is all relevant to the exposure, okay? So incident energy decreases as the distance from the arc source is increased, say. So obviously, you've got a neat little chart here in incident energy, but the key here, as you move away, as you get away from it, obviously, this is a no-brainer that as incident energy decreases, as the distance from that arc source is increased. Get further away, then that incident energy is less. So we do have different zones, and we have different work areas that you're going to look at and see as you're moving through 70E, because obviously it makes sense, right? So the further I am away from the incident, the further I'm away from the arcing source, then the incident energy is going to be reduced. So it makes sense. Move away, you get away from it, the energy is reduced. That's a pretty much common sense. But as a person moves closer to the potential arc source, as you get up in it and have to work on it, that energy increases by the square of the distance, okay? So 6 to 12 inches can be the difference between a serious burn injury and almost no injury at all. Really, seriously. 6 inches, moving it to 12 inches can make a difference whether or not it's a serious burn versus you don't even feel it, right? That can be a difference of as little as 6 inches, right? So workers must be aware of their body position and the working distance as they perform energized work. So if you are going to work on something energized, you have an energized work permit, there's no other way but to work on something energized. If that's the case and you have to work on it, obviously you're going to get a live work order to do this. But as you're working on it, you're wearing a proper gear, remember, distances matter. Okay, how close you are to the actual source as you move, and be aware of your distances, it's going to affect the amount of energy that's exposed to you over time. So kind of a summary here. OSHA mandates that employers protect their employees from recognized hazards. So if you're the employer and you know the hazards that are there, you've done a hazard analysis, you understand the hazards that are involved, then you have to make sure that your employees, all right, are trained and understand how to recognize those hazards. Okay, very important. And you have to identify them. That's what safety meetings do. That's where making people aware of what the hazard is of the day. And so that everybody has that on the forefront of their mind as they get involved in it. Now, the 3 recognized hazards associated with electricity are what? Shock, obviously, arc flash, and the arc blast. Right? The flash can be molten metal, can be bits and pieces of the bus. It can be the heat, the blast, all those type of things. That flash can burn. The arc blast can be concussionist, means it could actually blow you, could be so impactful that it stops the heart. It could knock you back. That blast itself could blow out your ears, could blow out, there's the 3 levels to be aware of. Any of those hazards could be fatal. And if not fatal, could cause life-changing injuries. And I can tell you right now, if you're in the middle of an arc blast and you end up having an arc flash, the blast itself blows everything into you, molten metal, the copper bus, whatever's there. And then, of course, the flash burns you to the point where maybe you have such severe burns and damage that you can no longer pick up your child anymore or do things that you normally would do. Maybe you enjoy playing golf or doing something, and then it can change your life in an instant. And for what? For a paycheck? It's not worth it. If your boss makes you do something that you know is unsafe, it ain't worth the paycheck. And if you think it is, you just keep doing you. But to me, it ain't. And I can tell you this, not just because I'm doing a video, knock on wood, I did a lot of work on switchgear. I did a lot of work. I wore equipment. I wore PPE. And every time I even did residential and I worked in a panel, obviously I always wore glasses, okay? But I always had gloves on when necessary if I was going to work on something live. Now, I turn off the main and I'm working in a panel or I'm roughing in something and I don't have any concern. But if I'm going to be working on live parts, and I'm going to be honest with you, you can say you do this all the time and you're a better man or woman than me. But even when I did things like hanging luminaires, going and doing a service call, hanging a ceiling fan, I turned the power off. There's no need for it to be on. But you do you. If that's what you want to do, you know what? I don't want to be one day you be a statistics and somebody gets there and says, told you so. Okay? That's not going to be something we want to be at. Next, the last thing, the electrical workers must use extreme caution when working on or near exposed energized conductors or circuit parts, as the hazards are present at all times. You saw that even normal equipment fails. Normal equipment can fail. And the gentleman I told you that was working in a panel, it happened so quickly, he can't even remember why it burned up or why it blew up and why the molten metal hit him in the eye. It happened so quickly that it affected him for the rest of his life. For what? Put on a pair of goggles. What's the big deal, Superman? You don't need to do that, right? Now, it says some electrical hazards may also be present only during some tasks, such as racking in circuit breakers in and out of their cubicles. That's true. So again, even when you're racking, you're thinking, okay, I'm outside of the equipment. This would be maybe in a big switchgear room and you're racking in or out big circuit breakers and you're cranking them in and out. You definitely have to have PPE on because it's getting ready to make or break contact. And if something's a ticking time bomb that's waiting, in that breaker, that something's malfunctioned or something. And the moment that it gets in there and makes contact, boom, something blows up, right? Or maybe you're cranking it in and some piece of metal that's in the framework falls down at the last minute. That's exactly how it can happen. And it can be devastating. Right now, about 95% of all arc flashes start out as phase to ground faults. Right? So just any of the phases, fault out the ground. Maybe the insulation is worn off. Maybe somebody's put a clamps on too tight. Maybe somebody didn't install a conductor properly. Maybe they didn't torque it right and it came loose and came in contact with a grounded part. Okay, 95% of those arc flashes start out as a phase to ground fault. Even though arc flash gets the majority of the attention, it is the shock hazard that injures and kills most people each year. Approximately 98% of electro fatalities are from electric shock. So while the arc blast is critical, while we have to wear proper equipment, it seems that people are still getting electrocuted. And I don't know why. If you're wearing proper equipment and you're taking the time, maybe it's because some project managers, people put too much stress on the electrician. It needs to be done too quickly and for cheap. Maybe companies don't even own proper PPE, and they should. Maybe they just haven't been caught by OSHA yet. They haven't had an incident. Who knows? But anyway, again, shock. Still, 98% of electrofatalities are from shock. But there's an awful lot of injuries from the blast, right? And it's just one of those things that in the flash, all those things, a serious problem. Okay, current flows through the body, even 115 volts or 120, as we say nominal, can be lethal. I think we showed that. And if you've ever been shocked, even if you're changing a luminaire or changing a fan and you've been shocked, well, you know what? People ask me all the time because I did a video using kind of like a gorilla ladder. And it's a metal ladder, and you can find that over on YouTube. And I said, Paul, are you saying that you use that metal ladder when you're working on lights or when you're working on something? I'm like, absolutely not. But if I am going to use that ladder, I'm going to make sure that the circuit is off, and I'm going to double check it. I'm not going to trust anybody else. Never trust anybody else. Verify it yourself. Lock it out yourself. Do whatever you need to do. If you're at a residence and you're still working on something, go to the panel. Shut that panel. If it doesn't lock, put duct tape on it so it can't open. And right on the duct tape, maybe say closed, leave closed, do not open, because you can always remove the tape. I don't want the homeowner or some of their kids or maybe the husband who's working on something don't realize that the wife called somebody there to do some work, and he goes in there and sees this and opens it up and turns it back on and say, that's why the power's off. It's not worth the risk. It just really isn't. So whether it's something as simple as residential, or obviously most job sites have a very strict safety policy, just make sure you follow the safety policy. Make sure you know lockout, tag out. You know, we're going to be talking about that in some upcoming videos, but really make sure you embrace it. And I would implore people that are own companies like Jay, like other people that own them, it doesn't hurt to have a safety talk with the guys once a week, once a month, once a quarter, however you want to do it. I know that on commercial sites, it's usually weekly, if not a little something daily. Take safety serious. It's not just for you, it's for your employees, but it's the families. That's the ones that are going to suffer the most. If I get killed from electric shock again, I die. But my families have to endure the pain of my death. In the aftermath. And that I could not bear to have them have to go through. Really. I'm going to be dead. They're going to have to endure it. Next, there's no such thing as a safe, energized electrical test. Absolutely not. Even that receptacle or that ceiling luminaire that you're going to be replacing and you do it hot, okay, there is no such thing as a safe, energized electrical test. De-energize it. There's no need to work on stuff live, Superman. You don't need to do it. You know, I'm in a hurry. Okay, whatever. But, you know, the moment something ever happens and you get shocked, maybe you just got this slight shock, but maybe it causes you to fall off the ladder and you break your neck. Was it worth it? Again, what we do as electricians is very critical stuff. We need to really treat it as such And that's all we were trying to do with this introduction. Not go too deep into the weeds, not too deep into the data. We got other videos that we're going to go deep, but we wanted to just make you aware that electrical safety is important, whether or not you're simply working on a service call for a receptacle or you're actually working on big switch gear. Okay? It doesn't take but 1/10 of an amp to kill you. It doesn't matter whether it's a switch gear or a little old receptacle. That's all it takes. Also, lastly, it says accidents are expected and unanticipated. Unexpected and unanticipated. You don't know when they're going to happen at any given time. Do you think those 160 people in 2018 that died went into work thinking that's what's going to happen today? No, nobody expects it. You can't anticipate it. Now, you can look at the environment and look at the work you're getting ready to do and say, you know, this could happen. So I'm going to look at all the possible ways to make sure that I'm going to be protected. That's the best way to approach it. And don't let anybody bully you otherwise. Okay? Since there's no way to know when an accident is going to occur, it is important to prepare at all times for what could happen. Know where the AED is. Okay? Know where the safety kits are. That's what you should be doing in your training sessions, your morning sessions. 10 minutes, 15 minutes. Make sure everybody verbally acknowledges that they understand where everything is and what to do if somebody gets hurt. Okay? We all want to get home to the families. Okay? So this includes safe work practices and procedures and using appropriate PPE when performing tasks that could lead to injury, right? Anything that could lead to injury, it's so important that you think about those tasks, right? So critical that you think about it, okay? All right. So we'll just kind of do this and get back to me here. We'll end on this as kind of an introduction. This is really for my CMECPs. Anybody else that listened or stumbles across this is great. We're going to be going even deeper into this. This was just basically a summary. This was an overview. We didn't get too deep into the weeds, but I wanted to hammer home, okay? Hammer home that it can happen at any time. And I know people have been hurt by simple 122 40-volt circuits, and I know people have been hurt by 40-volt circuits. And I know people because I've been there. When I was a young and dumb, I felt like I would be invincible, and I would work on equipment. But I happened to witness a fatality early in my career at a job site due to electricity. And the person was just very reckless. It's not like I thought something would happen. I wasn't like, well, that guy's going to die soon. He got careless, reckless, and maybe I'll share that story in another video. But I witnessed it, and it changed my life forever. And then when I started having a healthy respect for electricity, understanding that, dude, are you serious? There's a reason why we have GFCIs at 5 milliamps, right? There's a reason. And it's a real significant reason. And that's what Charles Dazell realized when he did his testing years ago, and it was spawned GFCIs. But there's so many other things that we encounter every day that GFCIs aren't going to help you with, right? There is no GFCI that's going to work when we're working in an electrical panel. Okay, we're working in switch gear. We're doing service calls. We're racking stuff in and out. Okay, we're doing service calls in bucket trucks, in parking lots, on lighting, and we're working in an industrial facility with a lot of metal around and everything's that's getting bonded and all this stuff, and people that don't understand grounding and bonding. People can do things in electricity that actually they think they're doing it right, and they're actually increasing a touch hazard. So we're not just talking about equipment blowing up. We're just not talking about normal operating equipment that fails. It's everyday safety that we just simply take for granted because why? Typically, we're not bonded good enough to have it really affect us. But the moment you're kneeling down, maybe there's a rip in your shorts, maybe your knees are exposed, maybe you're on a job and you're working on a piece of an HVAC equipment and you lean over it. Why do you think that they started requiring GFCI protection for outdoor air conditioning units or outdoor outlets, not receptacle outlets, but outlets in general? Why do you think that change came about? Because somebody got electrocuted simply leaning over a piece of HVAC equipment that was not wired properly. It wasn't that the equipment failed. It was not wired right. It resulted in a death. Well, There's no way easier to get things into the National Electrical Code than have it kill somebody, right? It gets in there really quickly that way. So at the end of the day, it changed our industry. So I guess that was the message that I wanted to give out to the CMECPs who are at a much higher level that I believe than anybody else. CMECPs go through rigorous 6 months of training. They learn the NEC inside and out. They get tested on it. They have a proctored exam. They have to do an essay explaining their knowledge of the code on whatever section they want. They make that commitment. So I guess I'll end on this. Anybody that's made it this long or watches this video, because I'm a long-winded guy, can't help it. It's just the way I am. You're not going to change me. No sense in giving the thumbs down or negative stuff. I know I've got my haters. At the end of the day, this was a summary to talk about safety because I just don't want to see electricians getting hurt. 160. I'm going to have a video that shows you what the current data is. We still have people dying. Why? We get too complacent. We go to panels so often. We go to service calls so often. It's that one time that we don't get complacent. That might be your last time. Dude, I love this trade. Electricity means the world to me. The electricians mean the world to me. So at the end of the day, when I look at something and see 160 electricians dead, I just don't, I can't wrap my head around it because to me, this is 100% preventable. Now, it makes it harder if equipment just blows up, okay? But when you're working around equipment, testing equipment, how about that study? 24% of the people that ended up getting injured was because they were doing what? Just testing, checking for voltage. Dude, don't need to be a hero. Get yourself a set of gloves, get yourself some safety glasses, okay? Even when you're doing the most mundane thing in a service, why? I know everybody's Superman, but if you end up knowing somebody like I know somebody that died from it, you'll realize that the reason I did this episode today, which is just covering the surface, and I didn't even get deep into anything about the arc flash, the arc blast, the boundaries, the ratings, the calorie ratings. That's for future episodes. I wanted to give you a little taste of why, to me, it's so important for electrical safety. Even today, I work on something in my own house. That breaker is off. There is no need for me to be a Superman. I'm just saying. All right, folks, I appreciate you all. Hopefully you enjoyed some of this, got a little bit out of it. All of our future videos will be down here in the fasttrackstube.com. Hopefully you'll subscribe and check them out. We're going to go deep into things as we look into the electrical safety, talking about 70E, OSHA, the ratings, the distances, all those details. I just wanted to touch the very top point of it, and we'll save all the details for another episode. Folks, I appreciate you. Thanks for coming to a CMECP Corner. All of you CMECPs out there, be safe and be superior like I know you are. And also, if you think you've got what it takes to go through 6 months of rigorous training in the CMECP program, pass a proctored exam, and pass an essay like our recent individuals, Jay Grunberg and Bill Butts, if you feel like you got what it takes, then go over to cmecp.org and read about what it takes and see if you qualify, and then reach out, and we'd love to get you in that program and get you certified as a CMECP. Till next time, folks, stay safe, God bless, and most importantly,